Hi, my name is Jody Burtis. I am a planetary scientist in the Applied Space Research Group at the Johns Hopkins Applied Physics Laboratory. I'm also the consortium co-lead for the In Situ Resource Utilization Group for LSIC. In addition to cosmic ionizing radiation, solar ultraviolet radiation also reaches the surface of the Moon and must be considered for both human and hardware safety. Ultraviolet, or UV, accounts for 9% of the total solar energy spectrum. The UV wavelength range is commonly subcategorized into 3 ranges. The longest wavelength portion is the UVA range, which spans from 315 nanometers to 400 nanometers. The UVB range spans from 280 nanometers to 315 nanometers, and the UVC range spans all wavelengths below 280 nanometers. Other categorizations for the UV spectra include the near UV range from 300 nanometers to 400 nanometers, the far UV range between 200 nanometers to 300 nanometers, and the extreme UV range below 200 nanometers. The extreme UV range is also referred to as vacuum UV, since it is strongly absorbed by the oxygen in air. While our Earth's atmosphere absorbs the vast majority of these harmful, high-energy UV waves, the Moon's exosphere is too tenuous to offer this type of protection. The lack of an atmospheric filter leads to UV flux on the Moon that is comparable to that experienced in interplanetary space. Therefore, the absolute flux and spectral quality of UV radiation on the lunar surface is much different than on Earth and far more dangerous. The expected flux of UV radiation on any given location on the lunar surface can be estimated from theoretical or semi-empirical solar models, as well as total solar spectral irradiance measurements by instruments like the solar spectrum and the solar auto-calibrating extreme UV spectrometer aboard the International Space Station. Be aware that literature reports for the UV spectral irradiance can vary due to measurement accuracy and the aging of spectrometer instruments in the natural space environment. Additionally, the incident UV flux at any point on the surface will vary due to a number of factors, including the Moon's orbital position and rotational period, the Sun's elevation angle, shadows, and UV reflections off the lunar regolith or other nearby hardware surfaces. UV irradiation can deteriorate the performance of materials and devices in variable ways. In polymers, for example, UV photons break chemical bonds that create numerous types of radicals via cross-linking and chain scission in the polymer structure, which leads to weakening and embrittlement. Other well-reported UV-induced effects include etching, color changes, darkening, and oxidation. UV also enhances outgassing from non-metallic materials, and any cooler surfaces nearby would serve as substrates for recondensation of these outgassed molecular contaminants. Furthermore, UV accelerates the curing and darkening of the molecular contaminants, which can obscure sensors and optical surfaces. Overall, long-term exposure to UV can affect the optical, mechanical, and thermal properties of several subsystems, including fabrics, blankets, solar arrays, cover glasses, lenses, mirrors, and radiators. The UV absorption on the material will depend on its chemical makeup, processing, and degradation state caused by all ground tests and combined lunar surface environments, such as temperatures, vacuum, and ionizing radiation. Both UV exposure and vacuum stability are fundamental requirements for all external surfaces, particularly those on optical instruments and thermal control hardware. Since biological molecules are efficient at absorbing high-energy UV radiation, the solar flux on the lunar surface can prove lethal to microorganisms, plants, and humans. In fact, the American Conference of Governmental Industrial Hygienists Standards sets a threshold limit value of terrestrial UV exposure to less than 20 minutes in order to avoid eye and skin injuries. Transportation units and lunar surface habitats must be equipped with protective personal equipment, filters, apertures, and other forms of UV attenuation. The outermost components of all lunar surface systems will need to be evaluated for UV exposure resiliency. It is ideal to select hardware that has been successfully used in other missions that involved space exposure, such as low Earth orbit satellites or the International Space Station. Keep in mind that the UV effects in these examples will be worse due to the presence of atomic oxygen, which is not a concern on the lunar surface. When searching for candidate heritage materials, be sure to decouple atomic oxygen effects from UV-induced damage to inform your selections. Additionally, consider the function of the exposed surface and what levels of UV degradation mechanisms can be tolerated. For example, discoloration and darkening of an external part of a lunar habitat might not be as detrimental as color changes in a thermal radiator or a solar array cover glass. Similarly, be mindful of assemblies that will be near optical instruments and other optically sensitive components, and assess their outgassing potential and temperature differences. You want to prevent outgassing products from getting adsorbed and UV cured on these critical surfaces. For more on this topic, visit the Vacuum module of Lunar Engineering 101, which provides an overview of outgassing and recommended mitigations. New lunar surface technologies might make use of novel materials with unknown response to UV radiation. Alternatively, you may want to employ traditional spacecraft materials where the effects of long-term exposure have not been investigated. These unknowns may be tackled with laboratory-simulated tests that make use of a suitable UV source and associated equipment for sample diagnostics, such as reflectance and transmissivity measurements. Several facilities have one or more of these sources accessible for partial or full spectrum UV tests. Some candidate sources include lasers, light-emitting diodes, deuterium lamps, mercury lamps, or mercury xenon lamps. You will want to choose a setup or facility that enables UV exposure in vacuum to prevent material degradation due to the presence of oxygen. Laboratory UV exposures may also cause material heating, so ensure the facility has the ability to monitor and control the test article temperature. An applicable reference recommended for further reading is the European Cooperation for Space Standardization Space Product Assurance Standard QST 7006 for particle and UV radiation testing for materials. Thanks for watching, and I hope this module has been informative.